Start the afternoon session, Professor Leandro Fiorini Aurichi. We will talk to us about how to use uniform continuity to move from a finite problem to a continuous one. Professor Leandro has a doctorate in mathematical science from University of Sao Paulo and currently works at the Departamento de Matemáticas del Instituto de Ciencias, Matemáticas y de Computación en la Universidad de São Paulo. His line of research is general topology, set topology, and graphs. Professor, you can start, please.
Okay, thank you for this invitation. We'll talk about something that's not very common to do in conferences, maybe because it's not something that's it's not a new result. It's a result that's old, very old one. Everybody knows this. This is part of any undergrad course about topology, right? At least about algebraic topology, which is not my field. But I every time I teach this course, I had the problem that I have to prove this in the middle of the course, and I always thinking that the proof that we usually do, or the proofs that are in every book or whatever, they are not very similar to the rest of the part of the course. So I was always wondering if we can do something more close to the general topology approach. So what we are going to do, first let me try to explain what we are trying to do here. So I will try to present an elementary proof that the fundamental group of the circumference is non-trivial. And I will do this very indirect way, but you're going to see that it's not hard, actually. And the most advanced thing that I'm going to use is that every continuous function in a compact set is uniformly continuous. So this is it's completely different from the proof that it's usually presented in the courses, right? So as I said, and see, for the point of view of somebody that works in general topology, this is the main result. I don't need to calculate it, to explicitly say that the fundamental group for the circumference is the integers, to show that this is not the same group as let's say the plane, right? Because the plane it's trivial. So I just have to show that it's not trivial. That's the part. So I will not calculate the group. So that's another thing that's quite different from the usual way. Because in the usual way, actually, instead of showing that's not trivial, you explicitly calculate what it is. You show that's z, that it's the integer. So this is another difference here. So let's see how we do this. The general idea will be that I will translate this problem to a finite one, so a very discrete one. So, and you can actually now you can say that is a very concrete one in the terms that are really concrete. I can make this with some wood and some lines, as you're gonna see. So I will translate the classical problem to one that's finite. And then I will try to show something about this finite thing, that I would show that in some sense this finite version is not trivial. And then I'm gonna use that we will also prove that the continuous version would imply that if the continuous version would be trivial, so then the finite version also will be trivial, which we will at that point we'll know that it's not true. So we have that, okay, the finite version implies the continuous one. We will show this each step very carefully. Don't need to worry about understanding what we are going to do right now, but this is the general picture. We will start with the finite version, then show how the finite version interacts with the continuous version, and then wrap up everything and have the result. So I'm going to start with 4 points. Let's say that they are A, B, C, D, and a notion that I will say which one is next to each other. So it's easier it's everything is written here, but it's easier if we draw a picture. So I will put the points here. So A, so point A is here, B, C, and D. Okay. So, and actually, I can make them. It's easier to make but sorry about this, because it's easier to, instead of putting it's easier to make the draws later. So I will just pretend that the points are all these parts. So A here, B here, C here. And now I'm going to say that A is adjacent to B, which is adjacent to C, is adjacent to D, and D is adjacent to A. So they make a circle. So that's just that. Okay. So 4 points, and they are very, very close together in this circle shape. But it's just 4 points. I'm not thinking about the whole circle. And then at some point, I'm going to need an end, which is this here, one here. And I will make a second cycle. In the second cycle, it will be exactly the same. So, but we will make this, and then now I will number them from 1 to n. So 1, 2, 3, 4, and so on. The last one will be n. And so I said that 1 is adjacent to 2, 2 is adjacent to 3, and so on. And at the end, the last one is adjacent to the first. So they make a cycle. I need these two things, and because of the way that I will represent that, that's not a part of the problem. I will call these guys nodes, and the previous ones I will say that this is a square, because I will pretend that this is a board game, which is better to picture this, but it's not important. Okay, so I'll call these letters squares, like in a chessboard thing. And this one that will make this, call these guys nodes. It will be more clear now. So what I will say, what is a configuration? This is part. This is important. So before we have these guys, which will be this A part, B part, C part. I will draw the inside because I think it's better for what is going on. So A part, B part, C part, and D part. So now I'm going to place these nodes from 1 to n in a way that it's valid. And what I say that's valid. Suppose that I put 1 here. Now the number 2 can be or in the same square, which I will represent like this, or it can be in the next one. So 3. Then I can put 4 here, which is in the same one. And then I can put 5 here because these two squares are adjacent. 5 here. I could put 6 here. And then I could put 7 here. I can put 8 here. And I can put 9 here. Okay. The important thing is that I cannot put, like, if I put 9 here, I cannot put 10 here, because this square is not adjacent to this one. So if 9 is here, the number 10 has to be or here, or here, or here. I have only 3 options. Actually, you only have 1 option that's forbidden. So I cannot cross in the middle, right? So pretend that this is just a line, and the length of the line is not enough to cross the circle. You have to go to just to another ones. So this would be a valid one, but actually I want to make a circle. So since pretend that 9 is my number, so my n. So I have to connect this one to the first one, which is okay here because 1 is here, so I can put here. So I moved from 1, 2, 3, 4, 5, 6, 7, and I only use 3 squares. I didn't use this, but that's okay. Okay, so this is a valid configuration. So configuration is just I put the numbers 1 to n in a way that I cannot have 2 numbers which are adjacent. They are not in squares which are not adjacent. Okay, so this is the only thing that will be forbidden. And now I will start with this valid configuration, and I will try to make another valid configuration, which will be just a movement from this. So it's like a board game. Suppose that you have this in real life, and then you're going to move this thing. Basically, I can explain this is just one phrase. The phrase would be, you can pick this configuration, move one of the nodes without breaking the lines. What that means is, it means that if I put, let's say, I will not draw everything here. So suppose that you have A here, B here, and I have one node here, another node here, and another one here. So it's like y plus 1, y plus 2. So this guy, see, it's adjacent to this one, this is adjacent to this one, and that's okay because it's A, B. I can move this one to here, can put here. That's okay because will be the three of them will be all in A, but I cannot move this one to C. I cannot do this. This is forbidden because it will be I plus 1 very far away from Y and very far away from I plus 2, right? It will be skip B. So this is not a valid move. So formally, this is just a function that assigns these things, and then you do the movement, and the movement it's again valid. And then the thing is that I just moved. The only difference from one to the other one is that one of the nodes change places. So in that case, would be this one, right? If I want to discuss where this one can move, I have to say where is y minus 1. So if it's here, then y can move here, can move in the previous ones if it's the same square, or can stay here. It can move whatever. I cannot move to C again. So that's the thing. So the most important thing is that, okay, I have a valid configuration. I move one node, just one, and I have to have a valid configuration again. I cannot break the lines intuitively. So this is a movement that is valid. Now I can pick any configuration which is valid. I'm only talking about valid configurations. And I will try to assign a value to that. For now, the value doesn't matter, but it's important that we can find this value. So everything here is trying to explain that in words, but okay, that again, it's more complicated. That way, it's easier if you draw a picture. What is saying here? It's saying just the following. The value, I will apply the value for the connection between two nodes. So let's draw all the possibilities, not all possibilities. Suppose that you have like two squares here. I have one node here and another node here. So suppose that this is y, this is y plus 1. I want to give a value for this connection. Okay. So how this connection will be? If this connection goes up in the sense that, let's say that here is A and here is B, it's following the order, then I give plus 1. So it will be plus 1. So this is plus 1. If you have a connection that in the other direction, well, suppose that the letters go that way, right? The letters go that way. So A, B, or C, D, E, A, that's okay. But then your connection goes downwards. It goes the opposite direction. So y here, in y plus 1 is here. So if you are in this situation, then you give this guy the value minus 1. And finally, if you have, you go that direction, but it will not make any difference, and both of them are in the same square, then this connection, you give a value 0. So if you go forward, you got plus 1. If you go backwards, you got minus 1. And if you stay in the same place, it's 0. Very easy, very simple. So this is what it's going on here. You have to explain everything in words, but in the picture is much easier. So the important thing is you have a valid configuration. So every time anything is connected to something or is in the same place, or go forward or go backwards. If you go forwards, plus 1. If you go backwards, minus 1. If it stays in the same place, 0. That's it. Okay, so this is the kind of connections we have. For any kind of connection, we have a value that is fixed, 0, 1, or minus 1. And after I have this value for every pair, I can give a value for the whole configuration, which is basically you just sum up every value of every pair. Okay, so every connection. So I'm gonna give you some examples, but you just pick the configuration. You have all the connections. You get value 0 or 1, and then you sum up everything. So two examples here. They are the two most trivial examples, and they are the only ones that we're going to use later. But it's good to understand this now. Okay, so this one. Okay, the first one is you have A. Again, let me draw this inside. A, B, C, and D. And here, everybody is in the same. So I don't know how many nodes I have, but everything is here. So this connection is 0, this connection is 0 because it's not going forwards or backwards. 0, 0, 0. So you sum up everything, the value is 0. That's fine. The other one is that you have just 4 nodes. Okay, so I'll draw here again the same picture: A, B, C, and D. And here I have the node 0, node 1, node 2, node 3. Sorry, because I started at the 1, right? But just let keep this notation. So 1, 2, 3, 4, and back to 1, right? So every connection goes forward. Remember that this last one is also forward for our convention. So this one goes here. So here is plus 1, plus 1, plus 1, plus 1. Okay, so the total here is 1, 2, 3, 4. It's 4. Okay, so this one is 0. This one is 4. So I just give the values for every connection, and then I sum up all the connections, and I have the total value of this thing. Okay, so and this is the two only examples that we are going to need later, but you can picture that we can have values for any kind of valid connection, valid configuration. Okay, the most important thing for these values is that this is invariant under the movements that I did before. What I mean about that? Suppose that I have a configuration. I will draw a picture here, but I will not explain everything. Okay, so just put it here, and I have somebody here, here, then they go back here, we go back here, another one here, and here. Okay, so what's possible to do here? One thing that's possible is to move this guy from here to here, right? This is valid. What else I can do? I cannot go here to there because we'll break this connection, but I can go this one to here because this guy is in this guy. So I can move this one backwards. This is okay. Okay, but the thing is that suppose that I have this configuration. I sum up the values. Okay, after I sum up the value will be some number. Let's say that we're going to be 4, which is it's true, but we don't have to check this right now. The value is 4. If I do these movements, the value again will be 4. I cannot change the values doing movements, valid movements. And then how we prove that is just looking for the cases. I would draw just let's say a couple of cases, and then you're going to understand what I'm saying. Suppose that I have it in the middle of this configuration. So here and here. And I will not put the numbers, but I will indicate what's going on. So suppose that this is the first one. So this link will be +1, and this one will be -1. So the total for this part is 0, right? Because +1, -1. I don't know what else is going on. But if I do this movement that go this guy back to here, everybody will be like this. So the total for these three guys is 0. Plus 1 minus 1, 0. Now this new position is 0, 0, which total is 0, right? So this is a movement. See, you don't change the total values because all the other numbers are not changing because you just move this one in the middle. All the other links have the same value as before. So, and these two links are the only two links that change something, but the total value of them is the same. So since the other links are really the same, their total sum is the same, and which is true also the same. So this is a configuration which would be possible. Another configuration that would be possible would be something like I have this guy here, and I go here. Suppose that we are going in this direction. So here is 0, and now it's 1. What I can do, I can move this point to there. But if I move this point to there, so the total here is 1, right? 0 plus 1, 1. After the movement, which is valid, is here and here. But now is 1 is 0, which the total is 1. You don't change anything. If you do all the possible cases, which is finite and not that many, you see that any kind of movement that you do, this total number, total value that we are giving stays the same. Okay? So what is going on here? See, well, I'm defining here what's the increasing configuration. An increasing configuration is something like that. It's easier to draw a picture again. Suppose that I go here. Next node would be or in the same square or in the next one. So I can put here, this is increasing. I can put in the next one, that's increasing. In the same one, increasing. The same one, increasing. I can go there, it's increasing. What I cannot do is go backwards. That's forbidden. So I always have to go or stay in the same square or go forward. Okay? And then you finish. If you have a configuration, this is increasing. This is increasing. Increasing. That's all I'm calling. I don't know what is the value. Actually, I know it's 4, but I don't need to know that's 4. I don't need to prove that's 4, which is good. We could, but we don't need. The thing is that it's very easy to see that since any of the particular values is or 0 or plus 1, this is strictly greater than 0. That's what I'm going to need. This is easy to see. Okay, so this one is 0. It's plus. It's greater than 0. And the other one is the constant one. The constant one doesn't matter where you are. Suppose that all the nodes are here, so they are connected here, but all the links have value 0, so the total is 0. So the value here is equal 0, right? So we know, because of that information that I did before, that if you start with some valid configuration, any movement that you do, preserve this value that you have at the beginning. And what I'm saying is that this kind of configuration has value strictly greater than 0, and the constant one is 0. So what it says? That there is no sequence of movements that you can start from here and get here. Why? Because everything that you're gonna get from here has the same value, which is greater than 0, and this one is 0. That's so we already proved the hardest part of theorem, believe me. So this finished the part of the finite version. The finite version just says that, okay, I cannot go from an increasing configuration to a constant one. Okay, see, I don't need to worry about if it's going looping around or whatever, because this will be more complicated than we need. We just need this part. That if it's increasing, has value strictly positive, and the constant one is 0. Just that. Okay, so we finished the finite case. Let's see the connection of this with the continuous part, which is that showing that the fundamental group of the circumference is as non-trivial And actually, you not even need to know what this word means because I'm going to explain. So what are we going to fix here? Suppose that it's trivial, let's say. So we're going to fix an homotopy, which is a continuous function from this to the circumference. So making a picture is from the square, the domain is the square, you get this age, and it gets some points here, okay? And two closed curves fixed from f and g. So the constant it's what if you get restricted this function restricted to this part, we're gonna make something here, and another one will be here. It's usually as what people draw the pictures like that. So this at the beginning. Now I will try to make this kind of cooperation will be discrete. So what do I do? First thing, this is just explain something that again is easier to explain in the picture. You pick the circle and divide that in 4 pieces. So the 4 pieces would be like this one. And don't do like my draw is like all the pieces have 1/4 of the circle, right? And I will name this one A, B, C, D. Okay, and I will say this piece is adjacent to this piece is adjacent to this piece, and this piece is adjacent to this piece, which here is easier to say. I said that 2 pieces are adjacent if they share at least one point. So these points have this point in common, these 2 pieces have this point in common, these 2 pieces have this point in common, and just these 2 pieces has this point in common, have this point in common. And actually, B is adjacent to B, but it's easier to say some stuff that I'm going to say later if you say that B is adjacent to B, which is all good. Okay, so we are in very similar situation that we did before, right? So this is the first part. Now I'm gonna need something that I should do some calculations here, but actually we don't need to, which is I will draw the picture again, I pick the pieces, and let's say that all the pieces have the same size. This is the infimum of the distance between a point in one piece and a point in another piece, which is not adjacent. So it's the infimum of the distance from the points that are here with the points that are here. With basically is this, right? In the picture is easier to see, right? So delta is this. This is the distance between the infimum of the distance between these guys, right? So since we are doing all this similar, it's the same one for any 2 pieces that you pick. So delta is this one, okay? And delta is greater than 0. Actually, here is the only reason why I split the square, the circle in 2 pieces, not in 3. If I do in 3, this is empty. I'm gonna have problems, and actually the proof doesn't work if I do this. But if you want to split this in 5, that's okay. This is exactly the same proof. But with 4 is the least number that works. So this is, I cannot do this, is okay. But 4 is what we are doing. Okay, so now I'm gonna use that. If you have a continuous function, so which is the homotopy, it is uniformly continuous. Which what that means in that case? It means that there is some R, this R will gonna be important later, such that if you have 2 points in the domain which are less, the distance between them is less than this delta. Sorry, if the distance in the domain are less than this r, the image will be less than this delta. Okay. This is uniform because I'm not fixing the x that's going to work here. It's for every possible pair. So here I use compactness, and I use that for compact sets. Every continuous function has this property. So this is the most advanced part of topology that you're gonna miss in this proof. So this thing. Okay, so I fixed the delta, and I use delta here to find r. So now I have this r. Okay, with how do I calculate this R? This R depends where the age function, the homotopy that we fixed. Okay, so now we're gonna use this R to do something. I will do. Remember that we have this square, right, which is 0, 1 times 0, 1. I will do this like a chessboard, but not in 8 by 8 pieces. We're gonna need lots of pieces. But I will explain this. So suppose that I did this. What is the size of the side of this square? I need them to be small enough in the sense that if I pick two squares which are adjacent to each other, the diameter of this figure has to be less than r, the r that we fixed before. So suppose that I have like one square and another square. So the diameter will be just this. This thing has to be less than r. So just what you do, you pick something like this, r, size of r, and then you put every possible ways to put these squares like inside. So if they are these like this, they have to fit here. But actually, I need another one which is harder because I'm saying that this guy is adjacent to this, not only this, and this. So it has, in the middle, you have 9 adjacent if you count itself. So I need this diagonal red. So I need that the square is small enough so they fit in this side R. Just that. So just pick L, let's say this size, this side is L, is small enough in a way that they fit like in R. So this is R, L. And now you have the number of squares that you need. Okay? So this. So you can calculate how small this L has to be, but I don't need this. I just need that it exists. Okay, so this is where we're going to use continuity. Suppose that I have 2 points in the square, which are in adjacent squares. Then their image will be in adjacent places in the circle. What I'm saying here. So suppose that I have one point here and another point here. Suppose that they are in this kind of situation. See, I'm already doing the proof. Okay, so if they are in this kind of thing, the distance between them, because of the way that we pick the size of the squares, this distance is less than r, sorry. So this distance would be less than r. So the image of these points, 2 points, in the circle is less than delta. But if they are with distance between, if the distance between them is less than delta, by the definition of delta, remember that delta is the smallest the distance between 2 points which are in places which are not adjacent. So if less than, they have to be, they need to be in 2 places which are adjacent or the same ones. So or we have this kind of situation, or we have this something like that. What I'm saying here, I'm saying that the only configuration which is impossible is that one point is here and the other point is here, because then the distance between them is too far, it's too big. That's it. Okay, so what I know is that if I pick points, any 2 points that are in squares, they are very close to each other, which are adjacent, the image will be or in the 2 points will be or in the same place or in 2 places that are next to each other. Okay, so this is where we're going to use continuity in this proof. Okay. So now I need to mark some points will going to be important for us. So I will draw the picture because it's much easier to say what are the points that are important. So let me do the grid of the 0, 1. So I started doing the important points like this. I put this one, this one, this one, this one, and this one. So in the corners, I pick the corner. In the edge, I pick in the center of the edge. So here would be exactly the same thing. Actually, which one here? Oh, sorry, this last one. I already pick a one for this square. So here, 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 and here. You don't have this one also. Just one per square. Okay. And in the middle, I just pick, okay, here I can pick this one, this one, this one. Here's the same. In the middle, I can pick whatever I want, so I pick the center. Okay. Oh, sorry. Bad drawing. Center, center, and center. So it's just 1 point per square. I make this the effort to pick these ones in the edge, the corner, and the other ones just in the side. And then the ones I pick in the middle. Just okay. So here's an explanation how I did this market point. So obviously I have only finitely many points marked in this square. But the most important thing is that I will go back to the picture, right? So most important thing is that suppose that since these 2 points, okay, so it's exactly the 2 points that I don't have. Sorry. Pick these 2 points. These 2 points, they are in square, which are adjacent. So their image will be or in the same place here or something like this, right? They cannot cross everything. So because they are adjacent here, they have to be, the image has to be adjacent. So that's it, because of the way that we fixed the delta and the R, okay? So suppose now that pick the below part of the square. And then you have all these things here. I will not draw everything, but just the below part and the upper part. I have this, and I have the special points. Special point, special point, special point, special point, special, special, and this one. And I have at the end special point, special point, special, 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 and this one. Suppose that here I have this function is cosinus and sinus, which is just going like this. Okay, they go like this. Start here and go like this. Okay, suppose that this function restricted to this part is this function that goes like that. And suppose that this last part is just the one that's constant here. Okay, so I'm assuming that this homotopy, we're going from the function that goes goes the complete circle, one full loop, and the other ones just stop it, right? What I have here now, let's pick the market points. Don't worry about the other ones, just the market points. If I go to the market points, see, the first market point is here, the image. The next market point, I don't know if it's in the same place or not. I know that it's upper, so go that direction. But maybe it's in the same one. Maybe it's in the next one. I know that's not here, right? The next one from this cannot be here because they have to be adjacent. But what I know that this is what we called before the increasing configuration, right? These market points, they go to a configuration here, which is increasing as we did in the first part. And this second one is everybody here, right? So it's the constant one. Okay, so what I have that this part, this is increasing configuration. And this part induces a constant configuration. Okay? So what I know from the first part, that it's impossible to make a sequence of movements from this one to this one, right? Okay, so let's do something here now. We are almost finished, right? Okay. So I need a picture better now. So just pay attention to this part. So I have this special point, special point, special point, and special point. Just with four is enough for showing this. I have this square, not the square here. I don't need to. So let's say that this is a configuration. Okay, so this is increasing. We already know the first one. The induces a first increase configuration here. But now, suppose that I'm gonna change. I will not use this square. I'm gonna use, so I remove this one and I change to this one, which is exactly above this one, right? But see, this point, it's adjacent to this, which is adjacent to that, which is adjacent to this. So this thing induces a configuration uh, which is valid again. I don't know anymore if it is increasing. Maybe it's not, but I don't care. I know that this is a valid configuration. Why? Because this is a valid configuration, because this one will gonna be adjacent to this one, which will gonna be adjacent to this one, which will gonna be adjacent to this one, which is adjacent to this one. So I don't know how this will be here. Maybe do something very strange, but it's valid. But what is the difference from the first one? This is a valid configuration. This second one is another valid configuration, and the only difference is these 2 points. What that means? This means that this is a movement from this configuration, for the first configuration, for the second one, right? This is a movement from the first for the second. Okay, so now we are in this situation. We have this guy, right? So now I can move this another one. I just make them exactly the same argument and change this guy to this. And I have this new configuration here, which is again a valid configuration, which is a movement from the second one. It's not a movement from the first one because I moved 2 pieces, maybe, right? But for sure is a movement from the previous one. So I have a movement, I have a configuration for the first, then I get a second one by a movement, then I get a third one for this, and then later I can change this guy for this, which is okay. Then later again change this, and then I'm gonna at some point I'm gonna have this one. So everybody goes up one level, and then I repeat the same thing, and then I'm gonna have this one for the next ones, and then I repeat everything, and then finally I'm gonna have this one. So what I'm saying that if I start with something below the very bottom line, this is a valid configuration. I can go by this movement step by step with valid moves and get to the final one. So if this first one was increasing, the thing here, we know that's impossible to get to the last one, which is constant. So if we had an homotopy between the function that's sinus, cosinus, or whatever, and goes
Profesor Leandro, can you hear me? ¿Fue mi internet o se congeló la imagen y el audio?
Yo tampoco lo escucho. Yo creo que debe ser el profesor Leandro.
Ok, vamos a esperar un momento. Esperemos que se vuelva a conectar. Está conectado, pero creo que no nos escucha. Voy a tratar de comunicarme con él, permítanme. Ok, parece que el profesor se quedó sin internet. Esperemos unos minutos. Son cosas que suelen pasar en estos eventos en línea. Entonces, pues demos oportunidad que regrese. Seamos pacientes. Creo que ya está de nuevo. Profesor Leandro, can you hear me? Profesor Leandro. Creo que el profesor sigue teniendo problemas con su internet. Les digo, vamos a esperar un momento, un poquito de paciencia, por favor.
Sí, claro.
Profesor Leandro, can you hear me?
Yeah, I got a problem here.
No problem, no
Sorry
problem.
about that.
You can continue.
But I have no idea what I was when I got the problem. Probably I was very at the end, but I don't know when because the problem I did realize very fast that. Okay, let me open this. So I was just finishing the what I where I think that was going, but just a second. Sorry about this. Let me just. Okay, so we can. Okay, so I think I was about here. So the thing was at the end, just to resume this thing, short version of that is that, okay, if you have a configuration which is below, you can change this valid configuration, which we're going to be this. We will do something in the circle, and then you change, just move one of these to the line that's exactly above that. So let's say that you have this point at the beginning, so you change for that. So this one again will be a valid configuration here. And then I can move this one from this to here. So I have this is adjacent to that, which is adjacent to this, which is adjacent to this. So again, will be a valid configuration. So every time I go one piece up, just one, I have a valid movement here. So if I start with something below and end here, because then if I go up every piece each time, at some point I'm going to have this. Then I can repeat the process and go up another line by movements. And I go up, go up, go up until I get the final one. So I'm going to have a list of movements that goes from the first one to the last one, which we already know that it's impossible if this first one is increasing and the last one is the constant function. Okay, any constant function. So if the first one is increasing, which is the cosinus and sinus is increasing, and the last one we fixed to be constant to 0. So we know that it's impossible to have a sequence of movements from the first part of the second. So if you have this homotopy from the anything that's non-trivial for the trivial one will be a contradiction. So we get this result, right? So this last slide is just saying that, which I just said, just explaining that you're going to have this sequence of movements from one thing to the last one, and then this will be the end. Okay, so thank you very much.
Thank you. Is there a question for Professor Leandro? Someone? We have some minutes for questions. Okay. Questions? No questions?
Leandro, yes, something I don't know. How is the non-elementary proof of that? Because you came up with this topological proof, but what do they do usually to prove this?
Usually to prove this, you need the covering space, and then to make the covering space actually how to go up to the covering space, you need lots of bar compactness. So okay, if you go like a waving hands proof, it's easy as well if you define what is the covering space. But to make all the details about the covering space, that the function that when you go up to the covering has just a unique point and then go everything there, it's more complicated. You need to be much more careful. That what
and you would say that these proofs, they are essentially different.
I would say so. Yes, because see, okay, obviously, to prove that spark compact, actually you're going to use something that's Lebesgue number, which also proves the continuous, the uniforms continuity. So at the end, what you're going to use is the same thing, but there you have to go more ideas, and here is more direct in some sense. I think.
And there is like no argument like that is a discrete part in the other version of the argument that you.
I would say that this is a discrete version of the other one, but the thing is that how we prove the discrete version, then it's completely different, right? Then that kind of invariant that we have, this is not what is done in the continuous version, right? So it's, you need Okay, let's say that the way that we move from the discrete version to the continuous function, you have some resemblance with this whatever, but then you have to prove the discrete version, whatever, or else you don't do anything. And this is completely different.
Okay.
Nothing to do.
Okay. Thanks.
Another question? If no more questions, we present the certificate of Professor Leandro. Let me. Okay. Thank you very much for your participation in this third International Congress on Topology and related topics. We send you the certificate by email. Again, thank you very much.
Okay, thank you. Thank you.
We start the next exposition in 3 minutes, please.